Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition, and we're doing problem number 7.5. It says air at 300 degrees Celsius and 130 kilopascals flows through a horizontal 7 centimeter inner diameter pipe at a velocity of 42 meters per second. Part A, calculate kinetic energy rate in watts, assuming ideal gas behavior. Okay, so this is the information that they gave to us here. Part A, they say calculate kinetic energy, assuming ideal gas. The ideal gas law is this. Okay, and equation for kinetic energy is here. In order to turn moles into mass, because they gave us the kinetic energy rate, we have to know the mass flow rate. In order to turn moles into mass, you have to use the molar mass of air. Okay. And in order to change our they gave us a velocity, but they didn't give us the volumetric flow rate, but they did give us the inner diameter of the pipe. So we can use the velocity times the cross-sectional area of the pipe to give us the volumetric flow rate. The cross-sectional area of the pipe, we assume the pipe's a circle, right? So cross-sectional area is a circle, pi r squared. The radius is 0.7, or that's the diameter, 0.7, because the inner diameter, right? 0.7, or 0.07, sorry, squared, divided by 4, because that's the diameter, okay, times pi, okay? Then we calculate what the molar flow rate is, okay, moles per second. Then we can calculate what the molar mass is, which is a weighted fraction with the mole fraction of air, which is assumed to be 0.21% oxygen and 0.75% nitrogen. So this is oxygen, nitrogen molar mass. So you weight those and you get air. Okay, and then you calculate what the mass is using our function right here, right? Okay, so now that we know the mass and the velocity, we can calculate the kinetic energy in watts. The kinetic energy rate, okay. 112 watts. Okay, part B. If the air is heated to 400 degrees Celsius at constant pressure, what is the kinetic energy change from 400 to 300? Okay, so this doesn't change. They didn't specify something else, right? So the question is, does the velocity change? In real life, it probably does change, right? If you don't change the pressure and you're heating it up, the gas is going to expand, right? And so I'm not sure if you're pumping the gas. It's kind of up to, I don't know exactly how fast this thing is flowing anymore, right? So we can't use the velocity, which is really important to calculating the kinetic energy. I don't know how that changes the velocity, right? So I can assume that the velocity doesn't change. In this problem, I don't know exactly what they mean. So I assumed that the velocity doesn't change so that we can calculate a kinetic energy. And if the velocity doesn't change, but the pressure is lower, or the pressure isn't lower, but the temperature is higher, so the volumetric flow rate is lower, then the kinetic energy is going to be lower. But you might be able to make a different assumption, and I'm not sure if you guys know, or if you have any comments or anything about how to do, what assumption to make here, because you need to make some sort of assumption that I didn't think of right off the bat when I was doing this problem earlier. So this is the one that I made, but there might be a better one. If you guys have something better, you can put it in the comments. You might be able to calculate something a little bit better than I have. So we do 400 minus 300, right? Okay, and the change is here. So you get a negative change because it drops, like I explained. Okay. And then part C, why would it be incorrect to say that the rate of transfer of heat to the gas in part B must equal the rate of change in kinetic energy? Okay, well, we can look at our kinetic energy balance, or just not kinetic energy balance, but the whole energy balance, right? So you have a change in enthalpy, you have a change in heat coming into the system and leaving the system, and then you have a change in shaft work, right? So there's a lot of things in here that they didn't tell us what they were, right? So it's kind of arbitrary. You could have different situations. They said that the pipe, is heated up, so maybe we know a little bit about Q, but we don't know what this is, right? So, we might be able to calculate what a change in enthalpy is for air, and then calculate, if the temperature changed, how much that enthalpy change was, right? So this would be some sort of non-zero number. So that means that basically they're saying, how come delta kinetic energy is not equal to just Q? Well, there's a few other factors here, and we know for sure that this one is non-zero, right? So these things are not necessarily equal to each other, okay? So if you assume that these are constant, then you could say that these are equal to each other, okay? So H is a function of temperature, so it's likely non-zero, right? And the shaft work might be different as well. We don't know how much work is going into pumping this fluid. If the pressure the pressure doesn't change, but the volumetric flow rate changes, maybe the amount of work it takes to pump the fluid is also different, right? So yeah, interesting question there. I don't know if I give the best answer. If somebody has a better answer, I'll pin your comment and just put it in there if you have a better way to explain this problem. But yeah, those are my thoughts on it. And thanks for watching the video. Hope you guys enjoyed. Hope to see you in the next video as well. Thanks.